So the next presenter are Doug Harshbarger. Doug Harshbarger is Division Vice President and Director of Automotive Future Technologies at Corning. He leads, he's looking for basically for new business in automotive market. He joined Corning in '96 and had multiple roles in engineering, product management, strategy, corporate development, innovation programs, so quite significant career. His key focus now is optics in the automotive business, and he received his master's at the University of Nevada. And the second presenter is Jae-Yong Chang. He's the vehicle solution planner from Keysight Automotive. At Keysight, he's responsible for future IVN test solutions, and also he's responsible for standardization. So he's trying to keep all interoperability tests and what Keysight is testing with their equipment, that he has also good impact in the standardization and also in the interoperability test specs to have very good products at the end of the day. He has a master's degree in physics from Sohang University in Korea. So, gentlemen.
Thanks, Thomas. Can everyone hear me okay? Yeah. Well, thanks to all of you for sticking around till the very last presentation of the day. And also thanks to the Bosch folks for organizing this great meeting and the IEEE folks for pulling it all together. It's been terrific. And I'm glad to hear there's such enthusiasm about the topic of optical fiber in cars from the last presentation. So what Jae-Yong and I are going to try and present today is some information about how we see glass optical fiber working effectively inside of a vehicle. Happy to take questions at the end. Maybe you'll get some of them answered from the data we're going to present during the presentation. Okay, so this work actually began a couple of years ago within Corning with a hypothesis. Our hypothesis was that optical communications, which has evolved to become a very mature technology in a lot of different markets, low cost and high performance and easy to use, was converging with trends in the automotive industry where the need for higher data rates and more flexibility in the system might make it appropriate, finally, for optical fiber, glass optical fiber in particular, to have a place inside the car. And so we launched a project to investigate that, and we've been at it for a couple of years now, engaging the industry, making prototypes, testing them, getting feedback, and trying to understand whether there's a fit and what the problems are. And what we found, first off, is that there are several areas where maybe a lot of experience with less modern systems of optical fiber have left misunderstandings or misperceptions about how the technology actually works and what it does well and what it doesn't do so well. And we've listed 5 of the things that we heard over and over again that were concerns with using glass optical fiber. Is there a need for the bandwidth? Does it address any real problems that we have? How does it fit the concerns that the automotive industry has? Is it affordable? Is it suitable? Can it meet all of the environmental and system requirements that are out there? And lastly, are there standards and tests that are going to allow it to be easily used by the industry? And I hope what you'll see at the end of this presentation is that we see modern glass optical fiber systems having technologies that are highly suitable for automotive applications. And we're ready to engage with the industry to try and make something that will make your lives easier. Actually, having heard the last few presentations on the copper system, wouldn't it be nice not to have to worry about the temperature changing, or how far your system is going, or whether the cable is good enough? All of those things are possible with glass optical fiber. I'm not going to spend a lot of time on this slide because I think everyone in the room understands that data rates in cars are going up, and that there are now standards available at very high data rates. As Bob said yesterday, if you build it, they will come. So now we have 25 and 50 gigabit per second automotive Ethernet standards, and we're looking for the applications that will use that technology. And we think they're going to come, and we think that optical fiber will play a part in it, in part because of the physics that we heard in the last presentation. This chart on the right, many of you have probably seen it before. It's been around since 2010. It basically plots applications for communications links using either copper technology or fiber technology. The brown triangles are the copper, and the round circles are the fiber, and it's plotted as a bandwidth or a data rate and distance, with data rate in the x-axis and distance on the y-axis. And so if you look closely, the green triangles are sort of agglomerated around a 10 gigabit per second times meter line, and the fiber ones are sort of around a 1 terabit per second times meter line, and in the middle is the 100 gigabit per second times meter line. And that's what we've noticed in many different markets that we participate in. That's the point at which people start seriously looking at using glass optical fiber, and where it starts to make inroads as a viable technology for a lot of different reasons. Obviously, there's points on both sides of the line, but that's kind of the thing that for us was the first thing that piqued our interest, because we see all of these different applications out there with high data rates for cameras, like I said on the last page, and other types of sensors and displays and everything, and you're actually approaching that line. In fact, the green box and the red box over there are examples we're aware of from vehicles that are on the road today and vehicles that are in development today that are right on top of the line. So right in the zone where people usually are seriously thinking about applying glass optical fiber technology. And so from a first standpoint, we think that network links are evolving to require the bandwidth distance products where glass optical fiber is commonly used. So the next topic is around fit. So I talked about bandwidth already, but part of our process was to look at what other trends are there and what other needs are there in the automotive industry. Things like weight reduction and size reduction, and making simpler harnesses and easier to install harnesses, faster development side, and sustainability. All of these things we heard over and over again. And what's our belief is that glass optical fiber actually has a role to make your life easier for each one of them. It is lightweight and has a small footprint. It can do millions of cycles in very tight bend diameters. It's inherently EMI resistant. And it has a multi-time lower carbon footprint, which becomes increasingly important as time goes on. So our view is that this can potentially be an even simpler solution for you going forward. So now let's get to the big question on affordability. So I always like to start this discussion with sort of a history. So fiber's been around for 50 years. That's a pretty long time. It's a long time for innovation to happen. It's a long time for scale-up to happen. And it's a long time for maturing to happen. And frankly, that's exactly what's happened. I've pasted on here a few different examples of some new technologies that have been introduced over this 50 years, mainly because I think they're directly relevant to the automotive application. A few examples, the zirconia ferrule in 1980s. That's what made it possible to make high-performance, really inexpensive optical connectors that are very reliable. The bend-insensitive fiber in the 2000s. That's what made it possible to have millions and millions of cycles with very low loss in an optical fiber. And then the last one at the end there, the high-density connectors and the pre-connectorized cables. Those are more recent things that have been used for fiber to the home and data center applications, but they're much more like what's inside of a vehicle now with complex wiring harnesses. In addition, what's been happening all through this time is the typical link length of a fiber link has been going down as the data rate goes up. And now we're in the area where it's common to install tens of meter or even single-digit meter lengths of fiber in a real-world application. So we think this is heading exactly where the automotive industry is landing as well. And the nice thing also about having all of these years of experience is that we've already developed standard products for the market. So an example of that is OM3 multimode glass optical fiber. So it's in data centers and in buildings all over the world today. It's a very robust and reliable technology, plenty of bandwidth capacity, hundreds of gigabit per second, over 10 meters. It's bend insensitive. It's available from suppliers around the world in high volume. In fact, this is exactly the fiber that was specified in the standard the last presenters were talking about. And by bringing to the market things that are already available easily and familiar, we feel that makes the path easier for the automotive industry to start bringing in these technologies. And I always like to include a few pictures because we get questions all the time about how robust and reliable the technology is. This is a technician in our lab basically holding a bowling ball up by a single glass optical fiber. It's very strong material inherently. Now, the next topic on cost, if you have the standards, then you can get high volumes and drive down the cost. And there's two charts on here, one addressing the fiber media itself and the other one the transceivers. On the left-hand side, it shows the cumulative volume of fiber since the beginning of the market. It's over 6 billion kilometers that are installed in the world right now. And annual capacity for fiber is 500,000 kilometers every year, many times what the automotive industry could ever hope to use in a single year. It's a very, very available product. And as a result of driving up that volume, the costs have come down. It's 40 times cheaper now than it was maybe when you were in university playing around with fibers for the first time. And then on the right-hand side, we're showing data about the transceivers. So in order to make a link work, you have to have the fiber. You also have to have the transceiver. This is data from a public source, light counting, showing the change in the cost per bit of Ethernet transceivers. Another miracle of driving volume through Ethernet is that you continually march down the cost curve and you see significant declines just since 2016, getting to the point where they're projecting cents per gigabit coming up in the foreseeable future. And so we think this together suggests that having affordable networks inside of a car using glass optical fiber is reasonable. Now about suitability. There's not a lot of discussion about whether or not the network can work inside of a car. We had some other presentations talking about thermal stability and link length and bandwidth and stuff like that. That's really not something that has to be worried about at all with glass optical fiber. The left-hand side of the page shows a demonstration we did at this event in Yokohama last year where we set up a 25 and a 50 gigabit link with 40 meters of fiber, 4 inline connectors, the max allowed in the standard. And you have a wide open eye with basically no problem whatsoever. It's a very, very robust technology. That brings you to the question of if the system works, how about in the environment that it has to work in? So that's a matter of testing the cables and the transceivers and everything according to the automotive standards that are out there. Things like temperature stability, mechanical stability, vibration, shock, things like that, chemical durability, combination of multiple variables. A couple of years ago, some other people presented a talk at this group when it was in Munich showing data from other applications, aerospace and defense and industrial applications, well drilling, things like that, which showed all of these things were possible. But obviously those solutions were not really a viable choice for inside of a car. They weren't inexpensive enough. They weren't made for that application. I'd like to share with you a few slides where we talk about some new data that we've generated on products that we think are viable for an automotive application. I'll start with the temperature stability test. So this is a simple one. We saw a little bit about it in an earlier presentation. Put your cable inside of an oven, leave it in there at a very high temperature for many hours. This shows 3,000 hours at 150 degrees C. We had 6 cables in here. And on the right, you see the results of the test. The attenuation, which is the key thing that you have to manage with optical fiber, has virtually no change over that entire time. It's a very, very stable product over temperature. We also have done the cycling tests with temperature and humidity together. I didn't bring that data with me here today in the interest of time, but basically the same result. Less than 0.5 of a dB change over the entire test. So super stable product. We've also done some work on chemical stability. So in this case, the test that's written into the automotive standards, which is written around copper cables, requires you to expose it to the chemical over a certain period of time and then run some current through the cable? Well, you can run all the current you want through to an optical cable. I won't tell you anything about how well it works. So what we did instead is all of the chemical exposure, and you see gasoline, brake fluid, transmission fluid, battery acid, all the things you would expect to run into in a car, spend the time in it, and then wrap it around a very small mandrel and leave it sit there for a couple of months. And what happens is, effectively, there is no degradation whatsoever in the cable over this amount of time. These cables can be made with modern materials to be very robust against chemical exposure. I think the last one that I have on the components of the system relates to the connector. And this is the one we get the most questions about, because if you look at a connector that's in your data center or maybe in your local area network, it's clearly not right for being inside of a car. It looks fragile. It is fragile because it's protected in so many ways. It's possible, though, to design a connector that can be both affordable and robust for use in the automotive application. We have a prototype of one that we show a picture of here. I'm just showing one part of the data that we've gathered on it. This is vibration testing. Again, we had 6 parts that we put through the US car level 3 test regime, and you can see over the time there's basically no change whatsoever in the attenuation through the cable. So another example of how the technology is robust, reliable. We think it's durable and handleable enough for use inside of a vehicle. So I think that's my last one, and I'm going to turn it over to Jae-Yong to talk about the test and standards.
Can you hear me okay? Okay. So thanks, Doc. I'm going to brief you about the optical test system and test requirements as defined by the IEEE 802.3CZ, the multi-gig optical automotive Ethernet standard just released this year. So as you build a communication link with transmitter, receiver, and channel or link segment, it is important that you ensure that each of the components perform properly, and then they are all compliant to the industry standards. So for transmitter test, transmitter is typically characterized using an oscilloscope, where there are 2 types. One is real-time scopes, and the other is equivalent time sampling scope, or in short, is sampling scope with a clock recovery unit. And for the most of the electrical physical layer testing, real-time scope is used, but the optical measurement testing, kind of de facto standard in the market is the sampling scope because of the capability to perform the reference receiver testing and the bandwidth and all the other performance keeping up with the fast optical measurements. And for channel measurements, network analyzer or VNA is typically used. And for receiver testing, there are a number of options, but 802.3CZ has chosen a bit error rate tester, or BERT, with a pattern generator built in to basically generate the test patterns, and with or without the stressed patterns to the DUT to see how tolerable your DUT is to this stressed input signal. And IEEE 802.3CZ has defined PMD test patterns and test parameters per each data rates and for transmitter and receiver test. So good news is that all these test parameters, test patterns are a lot leveraged from the existing Ethernet standards typically used in the data centers. But one major departure in the transmitter test is called TD-FARM. TD-FARM is an acronym of transmitter and distortion figure of merit, and it is a main metric of characterizing your optical transmitter. It is a measure of how the quality of your optical transmitter relative to the ideal signal. So it's basically measuring the difference between the ideal like square wave TD-FAM and the actual signals coming into the oscilloscope. And for transmitter test, the scope should provide all the measurement required to perform the test parameters. And for receiver test, the one main metric here is the stressed receiver sensitivity measurement. And what it is to measure the ability of your receiver to detect stressed or degraded signal. Okay, so as Doug mentioned, last year at the same IEEE Automotive Tech Days event in Yokohama, Keysight along with Corning, KDFAB, we showcased a proof of concept demo of a multi-gig optical automotive Ethernet. Basically, we used 53 gigabits per second of PAM4 generated by the arbitrary waveform generator and converted into optical domain, and is transmitted over a 40-meter long, you see that 40-meter long of a OM3 multi-mode glass optical fiber. And as you see, it's heavily stressed with the multiple turns and very sharp bends and twists and ties to stress. You can imagine, and the output of that fiber is fed into the input of the oscilloscope. And here's the capture, where you can see that on the left-hand side, this is very raw data without any digital processing. All we did is just using the force of the Bessel-Thomson filter inherent in the scope, nothing else. And on the right-hand side is TD-FAM reference equalizer applied. So the eyes got wider open, and even without this filter applied, the raw data gives pretty decent. This is transmitted over a 40-meter long, 4 inline connectors, very heavily stressed, as you can imagine, is the output of that. So this is a great opportunity for us to be able to demonstrate the capability and multi-gig optical automotive Ethernet system. Okay. Now I'm gonna.
Yeah, I guess we're just going to summarize here. So hopefully you found that interesting and informative. We feel we're excited, we're interested, we're ready to engage with the automotive industry with prototypes of products that we think are viable for use here. They have the bandwidth, they fit the trends and needs of the industry, they're affordable, they're suitable, and there are test standards and other standards available to use them. And we think now's the time. So we're happy to talk some more about it. I see Steve first in line up there.
I am.
Steve, go ahead.
Yeah, thanks. Hey, Doug, thanks to you guys. This is really good. So I may have missed this, so I apologize if I did, but you've described this fiber. And is this a relatively new development that was really focused on automotive, or is this kind of standard OM3 graded index that you've had for a while? I'm just trying to figure out what it is, that's all.
It's standard OM3, the fiber.
Okay.
The change that had to be made for automotive applications is really in the cable. You have to have materials that can handle those temperatures.
Right, okay. Perfect segue into my next question, okay? So I saw that you had a, like, what was it, 150 C heat test, and that the optical parameters didn't change. What about the physical parameters at that point? Was the cable more susceptible to damage at 150 C? Or not? I apologize, I just don't know how this stuff works.
It was more or less the same as it was when it started the test, although I'll say freely the results that we had suggest to us that there's some tuning we could do in the formulation for the cable, and we will.
Sure, so let's go in the other direction. And the reason I'm asking is my son is what they call a harsh environment mechanic. He works for the United States Antarctic Program in McMurdo Station, Antarctica, where it is so far below zero, it doesn't matter whether you're talking about Celsius or Fahrenheit. It's just really, really cold. And I'm just wondering how the fiber would react in a really cold environment like that, mechanically, not so much optically, if you have any data.
Yeah, so I'm sure there are fibers used today in those places.
I'm sure there are too.
And so we know that it's possible. We've made specialty cables for that. We've tested this one down to -40, which is what the automotive requirement is. There's no problem there.
Okay,
But,
no mechanical problem?
nope.
Okay, great, thanks. That's all I wanted to
Yeah.
know.
Can you say something about aging?
Well, we're in the process of doing the tests, like
Yeah.
you've said. And you saw the thermal aging test. We've done the cycling tests. What specific types of aging are you?
Then it's okay.
Okay.
Another question?
So I'm going to continue what Ramin was asking.
Yep.
He had to step
I
out.
didn't hear all of his questions because
No,
I was
no,
back there, so
no,
feel free to fire him again at
No
me.
problem. He had to step out. So some of us in the copper world will obviously wonder cost, upfront cost, and then cost over time, either repair or recertification, as Ramin talked about. So in some of your slides, you touched upon how cost is going down with volumes, which is great. But then, have you already done any cost comparison vis-a-vis copper, upfront and runtime costs?
We've done analysis like that in many different markets for many times. The ones that we've done related to the automotive industry, I'm not really free to share the results of them, but
Okay.
they haven't stopped us from doing this.
Okay. Okay. So what you're saying is cost-wise, if I can get that answer from you without you saying the real answer is costs are comparable. Is that what it will be?
I'll use a more general description. Our observation is that as data rates go up, cost for copper go up faster than
I
cost
see.
for fiber, and there's a data rate where there's a crossover. And
Okay.
we think 10 gigabits or so is the place.
Okay. Good to hear. When would you be able to make data like that public? Would it be in a year or less than that?
I think like the last presenter said, you know, we are not copper experts, and so we work with partners to
Right.
get that data. I guess, you know, we share it in the right environments. It just wouldn't be probably at a conference like this.
Okay.
But if you want
Understood.
to talk to us afterwards, you want to work with us on a project like that, we'd be happy to do that.
I would be happy to, but I come from a copper world, so that's a bias.
Well, listen, I'm a big believer in find the truth, man. So
I will. It's very intriguing, actually, and to be honest, if this is what it is and what you're presenting over time, this could put some companies out of business.
I don't know. I mean, my own observation, having started in the fiber business in 1996, is that there's room for everyone to participate.
Okay, good answer. Thank you, sir.
All right. Further questions? Here we go.
So I saw one of your presentation was talking about transceiver cost.
Yep.
Is that what's including the cost for the optical cable too, or it just was a transceiver?
I showed two things. One was the fiber, and the other one was the transceiver. Different data sets.
Okay.
Similar trends, but that if you're talking about his question about what I think about the trade, you know, the crossover point between and data rates, we always do a system level analysis, so including everything.
I see. Okay.
Further questions? Then thank you very much.
Okay, thank you.